Hi friends, in the last video we learned that the electric field due to a point charge, let's say capital Q, at a point at distance r away from it is given by E equals to 1 over 4 pi epsilon naught times Q over r squared. And if we keep another point charge at that point, it experiences a force due to this electric field, and the force acting on that charge is given by this electric field E due to point charge capital Q times the another point charge. Alright. So now let's suppose we have a system of n number of charges and we want to calculate the force due to all of these charges acting on this charge small q. So how do we go about it is we find the electric field due to all of these charges at this point, and then the force will be given by the electric field times this charge. Okay, so we know that the electric field is a vector quantity. So net electric field let's call this point P. So at point P, is suppose E bar, so it will be equal to the electric field due to first charge plus electric field due to second charge plus electric field due to third charge, so on and so forth, plus electric field due to nth charge. So E1 bar plus E2 bar plus so on and so forth up to plus electric field due to nth charge. And I can write force on small q F bar equals to this electric field due to this system of charges at this point E bar times magnitude of this charge. Now since the electrostatic force acting on any charge can be written as the electric field acting at that point multiplied by magnitude of the charge, the rest of this chapter is about calculation of electric fields due to different charge configurations. And today we are going to find out the electric field due to an electric dipole at a point on its equator. So what is an electric dipole? An electric dipole is a positive charge separated by a negative charge by some distance. Okay, so here we have a positive charge plus q and negative charge minus q, and distance between them is 2a, and we want to find out the electric field due to this dipole at this point P, which is at its equator or perpendicular bisector. Okay, so let's suppose that E plus bar is the electric field due to positive charge and E minus bar is the electric field due to negative charge. So we know that the electric field due to positive charge is directed radially outwards from the charge, and electric field due to negative charge is directed radially inwards towards the charge. So E plus bar is directed like this, radially outwards from plus q, and E minus bar is directed like this, radially inwards towards minus q. So the net electric field at this point P on the equator of this dipole will be vector sum of E plus bar and E minus bar. And since the magnitude of these two charges plus q and minus q is same, and distance of point P from both the charges is equal, the magnitude of E plus bar and magnitude of E minus bar is equal. Alright. So magnitude of E plus bar is equal to magnitude of E minus bar. Now let's suppose that this distance of point P from the center of the dipole is x, and distance from point A to P, or this negative charge to point P, is r, So distance from positive charge to point P is also r. Now suppose magnitude of E plus bar and magnitude of E minus bar is equal to E, and E is given by 1 over 4 pi epsilon naught times magnitude of the charges, which is Q, over r squared. Okay. So now to find out the net electric field at this point, we need to resolve E plus bar and E minus bar along two perpendicular components. So suppose this angle is theta, and three sides of these two triangles AOP and BOP are equal. So these two triangles are congruent. So this angle is also theta, and this one is vertically opposite angle to this one. So this angle is also theta. Then we can resolve E plus bar and E minus bar. So E plus bar is resolved into a vertical component E plus cos theta and a horizontal component E plus sin theta, and E minus bar is resolved into a vertical component E minus cos theta and a horizontal component E minus sin theta. And here we see that vertical components of E plus bar and E minus bar are directed opposite to each other, and since E plus and E minus have same magnitude, these vertical components have same magnitude too, and therefore we can cancel them out, and therefore the net electric field is in horizontal direction, and it is sum of E plus sin theta and E minus sin theta. So the electric field due to a dipole at an equatorial point E suffix eq is equal to sum of E plus sin theta plus E minus sin theta. Okay, and then we have the magnitude of E plus bar equals to magnitude of E minus bar, and that's equal to E. So I can write this as 2 times of E into sin theta, and in this triangle AOP we have sin theta equals to this opposite side divided by hypotenuse. So opposite side is A, so sin theta is A divided by R. Okay, so this is equal to 2 times of E, which is 1 over 4 pi epsilon naught times Q over R squared, and sin theta is A over R. So the electric field due to an electric dipole at equatorial point is 2 times of Q into A over 4 pi epsilon naught times R cube. Alright, and using Pythagoras theorem we can write this R squared as A squared plus X squared, where R squared equals to A squared plus X squared, or R is equal to square root of A squared plus X squared. Okay, so this is the magnitude of electric field due to an electric dipole at a point on its equator, which is at distance x from its center, and to show its direction we define a new vector quantity known as the electric dipole moment. So the electric dipole moment is denoted by letter P bar, and it's directed from minus q to plus q in an electric dipole, and its magnitude is equal to q times 2a. Okay, the magnitude of charge multiplied by the distance between two charges. All right, so in this formula of the electric field we can see in the numerator that there is 2 times of qa or q times of 2a. So we can replace this term by the magnitude of the electric dipole moment, and we can rewrite the formula as E sub EQ equals to 1 over 4 pi epsilon naught times P over R cube, where P is the electric dipole moment, and here we can see the direction of net electric field and direction of the electric dipole moment are opposite to each other, and therefore we can write this formula in vector form as E equatorial bar equals to 1 over 4 pi epsilon naught times minus P bar over R cube, where P bar is the electric dipole moment of an electric dipole and R is the distance of this point from one of the charges, which can be given in terms of x and a as square root of a square plus x squared. Alright? Alright. So I almost forgot to mention the special case. So in practice, we deal with very small dipoles like atoms and molecules. That's why the length of the dipole is very small compared to the distance of point from the center of the dipole. Alright, so the case we are dealing with is when x is very large compared to 2a or a for that matter. So here in this formula we have in the denominator r raised to 3 and r is equal to square root of a squared plus x squared, which can be written as a squared plus x squared raised to half. And then taking q of this, we get r raised to 3 equals to a squared plus x squared raised to half raised to 3, which is raised to 3 by 2. And then since x is very greater than a, we can neglect this a squared in comparison with x squared, and for this case r raised to 3 is nearly equal to x raised to 2 raised to 3 by 2, which is x raised to 3. And therefore we get the simplified formula for the electric field. So electric field due to an electric dipole at an equatorial point is equal to 1 over 4 pi epsilon naught times minus of P bar over x raised to 3, and where x is the distance of a point from center of the dipole.